final factor affecting the rates of SN2 and SN1 reactions is steric effects. And there are steric effects on the rate of the nucleophilic alkyl substitution. First, which we've already seen in our discussion on substrate structure, is branching at the alpha carbon. And the alpha carbon is the carbon that's directly attached to the leader group. So as we go from iodomethane to iodoethane to iodopropane, isopropyl iodide to butyl iodide, we go from methyl to primary. We've introduced one branch, one of those hydrogens has been replaced with CH3. Then we go to the secondary, we introduce a second branch. And we go to the tertiary, we introduce the third branch. We see that the rate of the SN2 reaction drops. So the SN2 rate is largest for CH3 versus primary versus secondary. The reaction rate for the SN2 reaction for the tertiary substrate is negligibly small, and we see the SN1 pathway instead. It's very common in chemistry to label, using the Greek letters, the positions adjacent to something we want to talk about. It's also done in carbonyl chemistry. So in the case of iodobutane, we would label our carbons alpha, beta, gamma, and delta. But we would also, if we had a ketone, we would label the carbon next to the carbonyl as alpha, and then beta, and then gamma. And if it's a ketone, then it would be an alpha carbon on this side as well. Right? So whatever is directly attached to the iodide is alpha. In this case, whatever is directly attached to the carbonyl carbon is the alpha carbon. So when we have branching at the alpha position, the SN2 rate goes down. And we've seen that already in terms of the substrate structure, where we know that methyl and primary go almost exclusively by SN2, tertiary goes almost exclusively by SN1, and secondary is somewhere in between, where you have to look to other effects, like perhaps the solvent effect. If it's run in DMSO, that might give you a hint that it's an SN2 reaction, whereas if it's run in methanol, that might give you a hint that it's more likely to be SN1. In addition to branching at the alpha carbon, which has a fairly large effect, branching at the beta carbon will also reduce the SN2 reaction rate. It's less pronounced because the steric hindrance is further away and therefore less significant. But it's real. So, for example, if you look at 2-dimethylpropane, also known as neopentylbromide. pentane, or this would be isopentane, and this would just be plain old N-pentane. So they had an isomer already, and when they isolated another carbon-5 species, they had to come up with another name, and they said, okay, let's call it new pentane. So this neopentyl system has a lot of steric hindrance in the beta position. It's got 2 additional CH3 groups branched at the beta position. It's a primary bromine. It's going to be quite slow, but the SN2 reaction rate is also slow. Means that although you might look at that and think that it would readily undergo an SN2 substitution reaction because of primary carbon with the hydrogen group, you're actually going to have a quite slow reaction. If you have a secondary substrate, and you introduce beta branching, you will slow the SN2 rate down. Reaction is likely to take over. So the bromide will leave spontaneously while the nucleophile is still trying to fight its way past those sterically bulky methyl groups to get towards the carbon. And you'll generate a carbocation intermediate. The rate is not affected by beta branching because the nucleophile isn't trying to come in and attack that partially positive carbon in the transition state. That will cause the product of this reaction, if you were to react this with water, for example, to not be the product of reaction you would expect. It will actually cause the product of the reaction with water to be a tertiary alcohol. Because this carbocation can be changed by one of those methyl groups shifting. This is called a carbocation rearrangement, and we'll discuss that in more detail later. So because we have slowed the SN2 reaction rate down and caused the SN from carbocation rearrangement, which is not something one has to worry about in an SN2 reaction. So alpha branching slows the SN2 reaction rate down dramatically, but you do have to be on the lookout for these neopentyl systems. This is kind of analogous to a neopentyl system. Because the neopentyl system will take what may look like to make the SN1 reaction the preferred pathway. Steric effect that's relevant is sterically hindered nucleophiles. Decrease the SN2 reaction rate. If, for example, you were to use tertiary butoxide, as your nucleophile, you would not get the SN2 pathway because of the steric bulk of the potassium tertiary butoxide. The tertiary is an E2 elimination reaction, and your product would in fact be an alkene and tertiary butol. Tertiary tertiary butoxide ion is only capable of acting as a nucleophile if the substrate is methyl. So you can make methyl tertiary butyl ether, MTBE, which was the solvent we used for extraction of triglyceride, by reacting tertiary butoxide ion with iodomethane. But that reaction will only go for the least sterically hindered substrate, the methyl substrate. Even if you react potassium terbutoxide with just an ethyl group, you will have introduced enough steric hindrance that potassium terbutoxide will not actually attack, the terbutoxide ion will not attack that carbon, it will attack the hydrogen in the beta position instead. And you will get an alkene as your product. And tertiary butanol. This hydrogen is much more accessible sterically than the carbon attached to the iodide because of the hindrance. Right? It's going to bang into that hydrogen frequently on its way to try to get to the carbon. And in this case, it will just react by pulling it off. So sterically hindered nucleophiles decrease the SN2 reaction rate. It's a less important factor than alpha branching. Right? The substrate, sterically hindered substrate, is the most significant decrease in the SN2 reaction rate. And beta branching, right? Beta branching also decreases the SN2 reaction rate, although by less than the change from a primary to a secondary to a tertiary substrate. Right? The closer you get to the reactive site, the more significant the reduction in the SN2 reaction rate. And beta branching put that steric hindrance further away from the reaction site, right? Rather than actually on the reaction site. Right? A beta branch and sterically hindered tertiary carbon attached to your oxygen, both of those are one atom removed from the reaction site, and so they would be expected to have somewhat similar effects on the rate of the SN2 reaction. And the rate of the SN1 reaction is not affected by sterics because the nucleophile is not part of the rate determining step, so it doesn't really matter if the nucleophile is hindered or if there's branching of the nucleophile. Once you form a carbocation, it goes planar and the carbon is much more accessible. So the next thing we will need to do is we'll need to